Hi everyone, welcome to the next JenTalk on statistics. This is JenTalk 8.5, an overview of basic statistics 2. Stats for interval and ratio data. So since part 1, where we were looking at nominal and mostly ordinal data, now we're looking at statistics that are slightly more sophisticated when you're collecting interval and ratio data. Much of the data we collect with Likert-type scales, which are typically interval-level data, use more advanced statistical tools to analyze their significance. So when you think about the Likert-type scales, we're talking about things like strongly disagree, disagree, neutral, agree, strongly agree, or maybe you don't have that neutral point. Let's say you want to know how different the means of two groups are after a treatment or experience. This is not based on frequency, like nominal data applying the chi-square test. Based on the mean scores of a variable compared between two groups. Comparing means applied. Here's an example. A learning disability specialist at a community college wants to see if the average algebra class final exam scores of students are affected by the learning strategies class they offer, intended actually to affect math proficiency. Upon completion of the algebra class, they compare the final exam scores from those who took the study strategies class to those who took algebra without the study strategies class. So they have the means for both. Which test compares to see if there's a significant difference between these groups? The t-test does this comparison of means between just two groups. Let's talk about the t-test. The t is the difference between two sample means, a comparison between two groups' means. We are typically hoping, or hypothesizing, that a treatment or experience will lead to a significant difference. This learning strategies class, we're hoping, will lead to a significant increase in those algebra scores for the students that took the learning strategies class. The t-test is only used when there is random assignment to these groups, a control and a treatment group. So in the case that I described before, you would have to actually randomly assign some students to take the learning strategies class along with algebra, whether it's before the algebra or after, it doesn't matter, and others randomly assign them to take algebra without it. If you want to compare more groups for more treatment experiences, the t-test will not do. I put treatment and experiences in quotes because in research we call these treatments. But going to a class, experiencing the thing that we think will affect change is an experience that we also call a treatment. So let's talk about comparing the means of three or more groups, if you have three or more groups that you're looking at. ANOVA, or analysis of variance, is the statistical test you will do. The ANOVA test is a method to determine if three or more sample means are equal to or significantly different from each other. If they're equal, then the treatments have not had an impact. If they're significantly different, now you know that one or more of the treatments or experiences have affected people. Similar to a t-test, but the t-test measures the differences between two groups, or two means, and the ANOVA looks at three or more groups. Let's look at an applied example of the ANOVA. Imagine you wanted to assess the effectiveness of two newer physical therapy methods that are designed for people with prosthetic limbs. Let's say you wish to try out two new methods compared to the traditional method with people who have received these prosthetic limbs. So you randomly assign people in your physical therapy practice to treatment 1, which is one of the new methods, to treatment 2, which is the other new method, and then of course to the traditional method, all being randomly assigned. Upon completion, you compare the average or mean scores on various assessments taken throughout the therapies completed with all three groups to see if there's a difference in effectiveness for the three methods. You may find that one of them is far more effective. You may find that all three of them are not really significantly more effective at the end. Maybe you'll find that midway or early on, one seems to be taking the lead, but after the 6-week time period or whatever it is that you've allotted, they actually all end up in the same place, then maybe they're all equal, but you see earlier results with one of them, and that may be something that matters to you. It may be something that doesn't matter. Stats that compare means. Here's a summary of the two that we talked about. Assessing a possible causal relationship may be your goal. Stats that compare sample means after a treatment or experience has taken place help assess if there may be a causal relationship between the treatment and the outcome. May be is critical to understand because we can never be 100% sure, but there may be a causal relationship in these instances. Comparing the mean scores of two groups, the treatment group and the control group, for example, allows you to assess if there's a difference. Now, it wouldn't have to be that you randomly assign people to a treatment and a control group. Maybe you randomly assign people to two treatment groups and you don't have a control. You could still do a t-test. You just have to explain why you don't also have a control group, and sometimes that's possible and perfectly acceptable. If you're comparing the mean scores of 3 or more groups, this allows you to assess if there's a difference between them due to the treatment or experience that they had, and they're really experiences or treatments that they had. And it could be 2 treatment groups and a control group. It could be 3 treatment groups. In that case, you're using the ANOVA.